Example 2. College freshmen from a wide variety of colleges across the U.S. participated in a survey where 61% reported that they are attending a college that was their first choice. If you took a random sample of 100 freshmen, how likely is it that at least 50 of those students are attending their first choice college? So it's saying at least 50, so that's a good thing to keep in mind for later. But let's draw this population. So here's my population of college freshmen, and 61%, so not quite half, but a little more than half. So 61%, that's our P, and 1 minus P is not quite 40%, but it's 39. So the other 39, they're not attending their first choice college, right? Okay, so now imagine taking out of that population a random sample of 100 students, 100 freshmen, and looking at the sample proportion and plotting that on the SDOSP. So SDOSP. 100 is still a pretty large N, so I'm going to go with that normal distribution. And I know that my SDOSP's mu, the mu sub P hat, this should equal P, and that's 61%, right? And what is my standard deviation of this SDOSP? Because I'm not just looking at, who's in here. I'm really looking at if I took a sample of 100 students, how good is my sample? Whenever you hear that, like how good is this sample, then you know you need a sampling distribution. Okay, and so I should probably find my SDOSP's standard error, right? So we call it standard error because it's a sampling distribution. And so here it's the square root of P times 1 minus P over N. And that's going to be the square root of 0.61 times 0.39 divided by 100, right? And I'll just look that up here. So square root of 0.61 times 0.39 divided by 100. So that's about 0.0488. So 0.0488. And so each jump here, so this little jump right here is 0.0488, right? So that's how big those little jumps are. Now I'm looking for how likely is it that at least 50 of these students are attending their first choice college. Now I could turn this into a percentage by looking at 50 over 100, right? So my the P hat that I've been given is 50 over 100, and that's 0.5, and I want to know how likely is this P hat. And so it's nice to find out where the P hat is, and so this is the raw score, but raw proportions, sorry, not raw score, it's the P hats. But it'd be nice to find the z-score, right? And so the z-score of 0.5 should be the distance between 0.5 and the mean divided by the little jumps. How big are my jumps? In order to find how many jumps away. All right, and so let's put that in our calculator. So 0.5 minus 0.61 divided by 0.0488. So we get negative 2.25. So here we're somewhere like this, negative 2.25. and this is for 0.5. Okay, and we want to know how likely is it that at least 50 of those students are attending that first choice college, right? When we say at least, this is the lower limit, right? That's the least, right? And so we're really looking for this whole thing, right? And so you could look that up in the back of your book, or you could say the proportion that p hat will be greater than or equal to 0.5 equals, I don't know if you remember this notation. This is from a fairly long time ago when we did normal distribution. Okay, so here we want to know, remember in Excel, they give us the negative side, so we would have to do 1 minus this little piece. So 1 minus norm s in order for standardized. That's how we get that z. And we put in our z, and we should get 0.9879. So very, very close to almost everybody. 0.9879. 0.9879. So almost 99%, almost, of our samples should have at least 50% of those students attending their first choice college. All right, third example. About 75% of the U.S. population owns a cell phone, and I bet that's growing. On average, what proportion of people would you expect to have a cell phone in a sample of 10, 20, or 40, right? So this is talking about the average proportion, right? So we're looking at the mu sub p hat. On average, what proportion of people would you expect? Well, for 10 people, it should be 75%, right? For n equals 10. What about n equals 20? Well, even for that, the sampling distribution's mean should be 75%. And what about n equals 40? Well, for that too, this should be 75%. So what it's getting at is that no matter how big or little your sample size, your mean of the sampling distribution doesn't really change. And that's similar to what we saw in the sampling distribution of the mean as well. All right, final example. So about 60% of married women are employed. If you select 75 married women, what is the probability that between 30 and 40 women are employed? Okay, so here we need to know we need to know that our actual population, and this is all married ladies, right? So, and 60% are employed, so that's our P, and 1 minus P is 40%, right? And imagine now taking samples of 75, right? So this is a SDOST for n equals 75, right? And 75 is still fairly large, so I'll assume normal distribution. What is the probability that between 30 and 40 women are employed? Well, we know that mu sub p hat is 60%, and we also know that the standard deviation of p hat is the square root of 0.60 times 0.40 divided by n, 75, right? And all of that under the square root sign. And so I'll just quickly put this into my calculator. Square root 0.6 times 0.4 divided by 75. And I get 0.0566. 0.0566, right? So this is 60. Okay. So what is the probability that between 30 and 40 women are employed? Well, first of all, it helps me to figure out what percentage is 30 women out of 75 and what percentage 40 women is out of 75. So let's call that p hat sub 30, right? So that's 30 divided by 75, and also p hat sub 40, that's 40 divided by 75. And if I want to just get it in decimals, 40 divided by 75, and 30 divided by 75. So that's 0.53 and 4. 0.4. 0.4, 0.53 repeating. Great. So I want to know these two sort of slivers, right? And about the distance in between here is about 6%. So if I go about 6 down, so this first one, and another 6. So this would be roughly 0.54, roughly 0.4 something. So, so let's actually find the z-scores of this. So z of 0.4 equals, so these are the p hats, these are the z-scores, is 0.4, 0.4 minus 6.6, all divided by the little jumps. And these little jumps are 0.0566. 0.0566. So let's see. Point 4 minus 0.6. This needs a parenthesis around here. Divided by 0.0566. Let's see if I did this right. 0.4. Okay, great. And that is a z-score of negative 3.5. Negative 3.5. Oh. 3.5. Okay. What about a z-score of 0.53, repeating? Well, I'm just going to forget about the repeating part, but it'll just be something like 0.5, I'll put a couple there, minus 0.6, divided by 0.0566. And that's negative 1.17. Oh, let's say 1.2. Negative 1.2. Negative 1.2. All right. So here's my big problem. First, I need to let me just color in what I need. Negative 1.2 and negative, somewhere out here, negative 3.5. So I'll say somewhere out here, right? So we need to know this area, okay? But there's no table that'll tell us just that area, right? So here's what we'll have to do. We'll have to take everything below this and then subtract out everything below that, right? Because then we'll get this entire area, including this infinite tail, and then take out a tiny, tiny little bit of it to chop that part off, to get it in between this part and this part. So, in order to do that, I'll use my norms dist. And remember, that will give me sort of the negative side, right? So let me put in my bigger number first, this one. And then subtract. So that's my entire area below z equals negative 1.2. So that's the entire area. And now I'm going to subtract out the little tiny sliver way over here. So area below z equals negative 3.5. Right? So I can just norms dist negative 3.5. And that should be a really tiny, tiny, tiny number. Okay, so I need to subtract this area out of this whole thing. So I take this whole thing, subtract this little sliver. And I get still roughly a very similar number. So 0.119, that's my area. So this area here, we can call it the probability where p hat is greater than or equal to 0.4 and less than or equal to 0.53 repeating is roughly 0.119, right? Let me just check. Yeah. So it's about 11.9% is the probability that between 30 and 40 women are employed. So that's the end of sampling distribution of sample proportions.